Hi class, nice to meet you again. So today we will learn the lesson number 2. This is the basic of the thermodynamics. And in this lesson, we will go through 5 parts. First is about the first law of the thermodynamics. Second is the equation of the ideal gas. In the first lesson, you also learn a bit about the equation of ideal gas already. So in this lesson, we just pass through it again. Third part, it is the second law of the thermodynamics. Number 4 is the pure substance and its application. And the last one is most air and the application. And again, as usual, to help you to get familiar with the vocabulary of the lesson, and also important that you need to speak right and pronounce right in order to everybody understand it. So now again, listen to me and repeat after me. Energy conservation. Energy conservation. First law of thermodynamics. First law of thermodynamics. Second law of thermodynamics. Second law of thermodynamics. Ideal gas. Ideal gas. Molecules occupy negligible space. Molecules occupy negligible space. Real gas. Real gas. Low pressure and high temperature. Low pressure and high temperature. Pure. Pure. Pure substance. Pure substance. Chemical composition. Chemical composition. Phase change. Phase change. To melt. To melt. Melting. Melting. To solidify. To solidify. Solidification. Solidification. To boil. To boil. Boiling. Boiling. To condense. To condense. Condensation. Condensation. To sublimate. To sublimate. Sublimation. Sublimation. Compressed liquid. Compressed liquid. Saturated. Saturated. Saturated liquid. Saturated liquid. Saturated liquid vapor mixture. Saturated liquid vapor mixture. Saturated vapor. Saturated vapor. Superheated. Superheated. Superheated vapor. Superheated vapor. Quality. Quality. Vapor power cycle. Vapor power cycle. Rankine cycle. Rankine cycle. Refrigeration cycle. Refrigeration cycle. Thermal efficiency. Thermal efficiency. Coefficient. Coefficient. Coefficient of performance. Coefficient of performance. Alright, so now we start the lesson. First, we will talk about the first law of thermodynamics. As you know, the first law of the thermodynamics. Actually, this is the different definition of the energy conservation law. And you learn about the energy conservation law. They call it the law of the conservation of energy, the same. You have learned it in a long time ago at the high school or even at the secondary school. They say that the total energy of an isolated system is constant. Energy cannot be transformed from one form to another, but cannot be created or destroyed. So it's clearly that the energy cannot, in an isolated system, cannot be destroyed or created, but it's just transferred from this form to another form. For example, it's from the electricity, or called the electrical energy, to the mechanical in the pump or in the turbine, or in the thermodynamic system, it transfers from heat to work. So the energy just transfers from this form to another, but it cannot be created or destroyed. All right. And for the equation of ideal gas, like last week in the first lesson, we already know that the ideal gas is the hypothetical gas whose molecules occupy negligible space and have no interactions. So it means they have the very few molecules, and at the high temperature and the low pressure, it cannot be interact. So that we define as the ideal gas. And again, ideal gas is just a hypothetical. That means it's not exists in the real. But for the real gas, we can consider as the ideal gas if at a very low pressure and a high temperature. As you know, at the for the gas at low pressure, the number of molecules is very small, and because it's a high temperature, so the distance between molecules is very large, so it cannot interact. So we can consider, in that case, the real gas we can consider as the ideal gas. And for the equation, you already know that is the PV equal to RT, that we write for 1 kilograms of the gas, or we for the amount of G kilogram of gas, we will write at the P time with V capital equal to GRT. And as you know, in this equation, P is the absolute pressure of gas, V small v, it is specific volume of the gas, and the capital V is the volume of the gas. T is the absolute pressure of the gas, G is the mass of the gas, and R is the we call the gas constant. And at Avogadro, we know that the R will be equal to R mu divided by mu. In this equation, R mu equal to 8,314, and we divide by mu. Mu is a molecular weight of 1 kilomole of the gas. For example, the mu of the oxygen is 32 kilograms, and the mu of the nitrogen is 28 kilograms, etc. So for a certain gas, if m is mass in kilogram and mu is molecular weight, so then the number of the kilogram moles of the gas we call N would be given by N equal to m divided by mu, and the unit is the kilogram moles. And in the molar volume, V is given by the small v equal to capital V divided by N, and we know that N is we call the number of the kilogram moles of the gas. So V is the total volume of the gas. So we got the PV, and V here is total volume of the gas will be equal to N1 plus N2 plus N blah 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 to NC, and time with R bar and T. And of course, in this equation is R bar is equal to 8.314 kilojoule per kilogram mole time with Kelvin degree. And from that we got the P is the total pressure of the gas will be equal to the PV of the small number. So that is an equation of the gas. Now we jump to the third part. It is the second law of the thermodynamics. So we know that for the first law of the thermodynamics, this law does not indicate the direction of the process. So we just write the formula of the first law of thermodynamics is Q equal to W plus delta U. And in this equation is Q, as you know, this is a heat. W is the work. And U, as you know, that internal energy. And the delta G is the change of internal energy. And for example, in a system, when delta U is equal, we will have Q equal to W. So in reality, so when we write the first law of thermodynamics in the equation like this, we can say that, okay, it means the total of heat can be transferred to total of work. And in reverse direction, we can change the total of work into heat. But in reality, it's not happen like that. For example, we look at the screen. We can say that heat cannot be transferred automatically from the low to the high temperature. It means the heat, it can transfer from a higher temperature place to lower temperature place, but it cannot be go in the reverse direction without any outside energy support. Or in the second picture, you see that heating water cannot be make the shaft rotated. Okay, it means the work it can be transferred to the heat. For example, you put the shaft rotated in the water. Later on, you can see the water will be warm up. So it means the work is transferred to the heat. But it cannot be in the other direction. It means the heat cannot be transferred in the work. So you can say that the first law of the thermodynamics doesn't explain many natural situations. So we need to use the second law to explain the nature situation as follow. So for the second law of thermodynamics, we got two statements. First is the Kelvin-Planck statement, or we call that is the heat engine statement. That means this statement is used apply for the heat engine, and you know that in the thermodynamics we focus on the study for the heat engine and the refrigeration. That is the two system. That's the objects of the thermodynamics. And last week we already give example like a motorbike or the internal combustion engine. That is the heat engine, and the refrigerator or air conditioner. That is the refrigeration system. And that is the two objects of the thermodynamics. So now we go in the first statement that is applied for the heat engine. Kelvin and Planck say that it is impossible to devise a cyclically operating device, the sole effect of which is to observe energy in the form of the heat from a single thermal reservoir and to deliver an equivalent amount of work. Or we can say in the short form, it is impossible to build a heat engine that has the 100% in the thermal efficiency. Alright, so you look at this example. So Kelvin and Planck saying that it is impossible that you only use one source. You already know that we got the heat source and the cold sink. So impossible that we just use only the heat source to provide Q for the system, and then in this case, if it is real, W will be equal to Q as the equation of the first law of thermodynamics. We can have it in case of the delta U equal to 0, we got Q equal to W. But in reality, it's impossible to make Q equal to W. So that is the second law of the thermodynamics. Okay? So that's why we got the idea of the thermal efficiency. For example, you look at the diagram of one heat engine. We got a turbine here. First we got a boiler. The boiler receives the heat from the hot source, Q in, and that steam will go into the turbine, and the turbine create the work W out, and then it have to transfer the part of the heat into the cold sink. In this case, it will go into the condenser, and this condenser, it will release the heat to the cold sink with the amount of Q out. And that is go back to the pump. It's receive a work W in and go back to the boiler and make the cycle. So we got this is a cycle of the work engine. And because it received the heat Q in from the hot source and release the Q out to the cold sink. So in this case, we got the thermal efficiency defined as mu equal to W out minus W in divided to Q in. And you can see that because W in smaller than W out, so we can ignore the W in, because you know that W in just the amount of work consumed by the pump, and this amount of work or the amount of energy is very small compared to the energy created by the turbine. So in this case, we can in this formula we can just ignore the amount of the W in. So we can rewrite the formula as mu equal to W out divided by W in. And it will be equal to 1 minus Q out divided by Q in. And you know that because the Q out is the release energy, so it got the negative value. So in this equation, we just consider the absolute value. So we put in Q out in the absolute symbol. So it means we got the mu equal to 1 minus Q out divided by Q in. So the statement of the Kelvin and Planck saying that this we need Q out and Q in. So that's why Q out must be different from 0. So it's mu here, definitely it's smaller than 1, or it's smaller than 100%. So that is the statement of the Kelvin and Planck is applied for the heat engine. And this example show you that it will violate the second law of the thermodynamics. I mean, the same picture you have in the previous slide, but in this case, you see that there's no condenser here. That means there's no heat released to the cold sink. So it means this engine, it definitely cannot be happen, because if happen, it means it's only release it only receive the heat from the one source or one energy reservoir. So if this happen, you can say that the Q in equal to W. So it is violate the statement of second law of thermodynamics. So if we go through, that is the statement for the heat engine. So we go to the second statement of Clausius. So we call the Clausius statement. So Clausius statement, it is applied for the refrigeration system. So the statement say that it is impossible to construct a device which operates on a cycle and produce no other effect than the transfer of heat from a cooler body to a hotter body. Okay, so look at this example. So here, it means it receives the heat from the cold sink and it transferred to the hot source. And this happened, I mean, there is no work, the outside work provided to the system, and in this case, Qn will be equal to Ql. That is impossible. All right. So the Clausius statement that it is impossible that you can transfer the heat from a lower temperature place to higher temperature place without consuming any outside energy. That is about the Clausius statement. And again, look at the diagram of refrigeration. We got a compressor here. It will compress the air to the high atmosphere and high temperature. It go in the condenser, release the heat to the hot source, amount of QH, and after that it go to expansion valve, go down to evaporator. At evaporator, the substance will evaporate and it absorb the heat from the cold sink. So this is the diagram of the refrigeration system, and the diagram it will be represent in the PV diagram as the next picture. And we got the coefficient of performance of the refrigeration. We call the epsilon will be equal to Q2 divided by absolute of W. And as you know that we already defined that the work produced will have the positive value, and the work received will have the negative value. So in this case, that is the work received So we just use the absolute value. So we put in the absolute symbol. So epsilon will be equal to Q2 divided by absolute Q1 minus Q2. And again, because the Q1 is the release heat, so it have negative value. So in this case, we just consider the absolute amount. So in this case, because we got the Q2 divided by absolute of Q1 minus Q2. So this is the value cannot be infinity. All right, so that is the second law of the thermodynamics. Now we go into the next part. That is the pure substance of the applications. So what is the pure substance? These pure substances are defined as the substances that have a fixed chemical composition. Okay, so the chemical composition of this substance have the fixed, it's not changed. For example, for the water, we got the formula is H2O. That is the formula of the water. So this one is fixed, fixed. It's not changed. So that means we call the water here is the pure substance. Okay, so that is one example of the pure substance. So normally we go through the pure substance is the water first, and then this will be applied for all the substance like the refrigeration that you use in the refrigeration system. It's also the pure substance. As you know for the long time that every substance can be exist in the three phase. Depends on the temperature and the atmosphere. Okay, so we call that is the liquid, the solid, liquid, and the gas. So it's just depend on the temperature and the pressure. The materials of the substance can be exist in the natural and the different form of the phase. And the process to change from this to one phase to another phase will have a different name. For example, from the solid to liquid, we call this procedure is melting. Okay, melting. For example, we got the ice. You know, ice that is the solid form of the water. So if you put the ice outside the refrigerator, that means you put in the normal temperature of the atmosphere, the ice starting melt. So we got the procedure changing from solid to liquid phase. We call is the melt or melting. The opposite process, that means from the liquid transfer to the solid, we call the solidify, and now it's solidification. For example, you put the water into the refrigerator, and later on the water will be solidified and become the solid. Alright. So now when the liquid transfer to the gas, we call that procedure is boiled or boiling. For example, when you put the water into the oven, and later on the water starting boil. So when it boils, it starts changing form from the liquid to the gas. The opposite procedure, when it changes from gas to the liquid, we call the condense, or now is condensation. And if you see at a certain pressure and the temperature, or we can say at the very low temperature and low pressure, a solid can be transferred directly to the gas without go through the liquid. Normally, materials could transfer from from solid to liquid and the gas. But in a certain pressure and a temperature, it can be transferred directly from the solid to the gas without the liquidation. So the procedure to change from the liquid directly to gas, we call to sublimate or the sublimation. All right. Now we just look at the normal atmosphere. That means the materials will go through from the liquid to the vapor. Okay. So it's not go directly from liquid to the vapor, as you will learn this subject in Vietnamese. It will go through first we call the liquid. For example, now we at state 1, the water at the 20 degrees, and at the atmospheric pressure, that means the 1 atmosphere. We starting heating the water, and the water become heating up, and when it go into the 100 degrees at the 1 atmosphere of the pressure, the water starting it become the saturated liquid. Okay, so from the saturated liquid, the water starting to evaporate. Okay, it start evaporate. So you can see that if state 1 here is a liquid, state 2 we call the saturated liquid, state 3 it is a mixture of the saturated liquid and the vapor mixture. Okay, so this the state 3, it is a mixture. You look at the example here. It is the state 3. You got the saturated vapor and the part is saturated liquid. So it is a mixture of the saturated vapor and saturated liquid. So this is a state 3. And then we continue to provide the heat, and later on, when all the saturated liquid transfer into the saturated vapor, we got state number 4. So state number 4 here, that means there's no other liquid in the state or in the vapor anymore. So it purely 100% of the vapor. So in this stage we call the saturated vapor. All right, and then when it already reached the saturated vapor state, if we continue to provide heat, it will move to state 5, and state 5 here we call the superheated vapor. Okay, so at the so that is the to summary, when we heat up the water or any pure substance, it will go through 5 states. We call first is a compressed liquid, second is saturated liquid, third is saturated mixture, that means the mixture of vapor and the liquid, saturated vapor, and the last one is superheated vapor. And if we do it in the different pressure, at the end we got this diagram. So this diagram, first it got the 2 main light here. The light in your left hand we call the saturated liquid light. That means this light is the combination of all states of the saturated liquid. So we got the saturated liquid light. And in the left hand, we got the saturated vapor light. That means the combination of all the saturated vapor points. And at the point when the saturated liquid line and the saturated vapor line meet, this point they call the critical point. All right. So these two lines divide your diagram in the three zones. The left zone here we call the compressed liquid region. The second region that in the between two lines we call the saturated liquid vapor and region. And of course the last one, the left of the saturated vapor line, we got the saturated vapor region. So if it means if you look at this diagram, you can see there is the 5 states. So state 1 definitely it will be in this area. State 2 will be in the saturated liquid line. State 3 is in the saturated liquid and vapor region. State 4 it is the saturated vapor line, and state 5 it is the superheated vapor region. Okay, it's just in the different temperature and it have different pressure. So now the properties of a pure substance. So how to determine the properties of the pure substance? There are 2 ways to determine. The first is we use the table. So there are 2 tables, we call the 2 property tables, to determine all the 5 states. Of course, you know that our target is to determine the property of all 3 states here. State 1, state 2, state 3, state 4, state 5. So for the compressed liquid at state 1, we will use the table they call the properties of the compressed liquid and the superheated vapor. Okay, so it means you use the table, the first kind of table, to determine the property of state 1. For the state 2, state 3, state 4, they call the saturated state, we use the second type of the table, we call the properties of the saturated. So of course, for the saturated liquid, we have it in this line. For the saturated vapor, we got in this line. And for the point 3, you know that is a mixture of the liquid and the vapor. So of course the liquid here, there's no vapor exit. So in this case we call the quality X equal to 0. Whereas in form of saturated vapor, there's no liquid exit. So in this case the quality X will be equal to 1. So it means state 3 will have the quality X between 0 and 1. So it means in order to define or to determine the property of the state 3, beside the property that we can find for the state 2 and state 3, we need to know the qualities X of the state 3 in order to determine the property of this state. The last one, for the superheated vapor at state 5, again we use the table that we use for state 1, that calls the properties of the compressed liquid and the saturated vapor. And for the table of the properties of the compressed liquid water and the superheated water vapor, we need 2 independent properties. As you learned in last lesson, you know that in order to determine one state, we need 2 independent properties. So in this case, we need 2 independent properties, that is the pressure and the temperature. So when we know the pressure and the temperature, we can find out other properties like the specific volume, enthalpy, and the entropy. For example, you look at the table here, we got the first column, this is the pressure, and in the row, that is the temperature. So for example, you know the water at the pressure is 1 bar and the temperature is 100 degrees. You look at this table, you find out all the property. Like example, we got the specific volume V here, we got the enthalpy I and the entropy S. And then because you know there is total 6 we call the 6 properties, including pressure, temperature, specific volume, enthalpy, entropy, and the internal energy. So for internal energy, the Regard formula is U will be equal to 1 minus P PV. So we can find out the internal energy of this point. Okay, so that means for this table we find out the state 1 and state 5. And for the state 2, 3, and 4, we use the table of the property of the saturated water. And for this table, we got 2 different kind of table. It depends on the temperature. I mean, if we know the temperature, we use this table. So the second type of table will be the pressure table. So it depends on whether you know the pressure or temperature. We will use the respectively table. Okay. So again, in this one, when you know, as you know that for the state 1, for the state 2, 3, and 4, it's the temperature and the pressure is the 2 dependent properties. So it means when you know the temperature, you will find out the pressure. In opposite way, if you know the pressure, you will find out the temperature. So there are the 2 dependent properties. So in the temperature table, we got the temperature here. We find out the pressure and other properties like V comma here, or the V double comma. That means the specific volume at the in the saturated liquid line. V double comma, that means it is saturated vapor in the saturated vapor. And the row, that means the double comma here, that means indicate this is a property for the saturated vapor. And 1 comma here is indicate the property for the saturated liquid. And you can find out all the things. And of course, R here, they call the latent heat. I mean, the R here will be equal to I double comma minus I 1 comma. So this is they call the latent heat or the latent energy. I mean, the energy that's required to transfer completely the substance from the liquid form to the saturated vapor form. And here is just one example. For example, we know the temperature as 20 degree. It is the saturated liquid. And from the table, we find out that at the saturated, the 90 degrees Celsius will be equal to 7.183 kilopascal. And other like specific volume, we find out that is because it's a saturated liquid, so you use that the small v will be equal to v comma, and this is the amount of that. And then if the total 50 kilogram of the saturated liquid in the tank, so we time with 50. So in this case, we find out the volume of the 50 kilogram of the saturated liquid. Okay, so that is about the pure substance and how to determine the property of the substance. Now we applied it into the two cycle we call the vapor power cycle, or we call the Rankine cycle, and the refrigeration cycle. And this one is one picture showing you that it is they call the thermal power plant or the electrical power plant. And ECU coal here provide coal to generate steam, and the steam will go into the turbine and make the turbine rotate. The turbine will connect to the generator. The generator run and produce electricity, and electricity will be transferred to the electrical line or electrical grid. And then after the steam go through the turbine, it needs to go down to the condenser. This is the coal sink in order to condense, and it's the condensate. It's go back to the steam generator, and it have the one cycle. And of course, the exhausted gas or the cold combustion gas will go to the stack and just release to the atmosphere. Okay, so this is the diagram of the thermal power plant. And this one we call the Rankine cycle. So the steam generator will provide the steam to run the turbine, and the turbine will provide the work. I mean the work to rotate the generator to produce electricity. And after that, the steam will go back to the condenser, and it will release the heat. It will become the condensate, and it go back to the boiler by the pump. So that is the picture to show how the thermal power plant is work. And for the thermal power plant, of course, we will use the thermal efficiency to find out how good or how efficient the thermal power is. So we got the μT equal to W1 minus WP. WP is the power consumed by the pump divided by the Q1. And so in this case, because W1 is the work produced in the procedure 1-2 here, so it will be equal to enthalpy I1 minus I2. Okay, so for the pump, that is the energy consumed in the process 3 comma. So we got I3 comma minus I3 divided to Q1. So Q1 is the energy received in the procedure 3-1. So it's going to be equal to E1 minus to E3 comma. And for the refrigeration cycle, for example, we got the air conditioner here, and this is a window. We call it window air conditioner. Okay, so it means we got the fan here. I mean, the inside we got the evaporator, and the air will be run from the room. I mean, the hot warm air from the room will be observed to the evaporator, and it will be cooled down and go out at the cool dry air. And in order to increase the heat transfer coefficient, they will use the fan or the blower in order to make the air in the room is run faster. We call it a forced convection heat transfer. In opposite side, I mean the outside, we got the condenser, and again, in order to increase the heat transfer procedure, they will use the fan here, and of course we got the compressor here. So that is a window air conditioner. And here the picture, we got first the compressor we compress the gas from the stage 1 to stage 2. After that, at stage 2, the gas will go into the condenser, release the heat to the atmosphere, and it's become the condensate at stage 3, and then go to the expansion valve. We got the procedure or the process is 3, 4, and the end is from stage 4. The gas go to evaporator. It will be evaporate, and it will observe heat Q2 from the cold sink, and the procedure or the cycle is start again. And in order to know how good the refrigeration system works, they use the COP, it stands for the coefficient of the performance. It's epsilon equal to Q2 minus for absolute of the W of the compressor. Okay, so that is about the second lesson in the thermodynamics. And after this lesson, beside the some multiple choice questions as requested by the school, I will provide you the homework. That means each of you will receive about two or three pages of the subject in the thermodynamics, and you need to transfer it into Vietnamese, and in opposite way. I mean, you receive the document in Vietnamese and you need to transfer it into the English. Later on, I will upload this exercise or this homework into your BK e-learning, and you need to download it and do it at home and submit it to me. Okay, so thank you and good luck.